So today we're going to start looking at the eddy current probes themselves, the pieces of equipment that are used for eddy current testing. And so here on this screen is primarily laid out are a selection of probes. Also shown here are the cables or the wires that that hook up to them. So there's three kind of cables or wires shown here that would be used to attach your various probes. Everything else on this page is some kind of an eddy current probe. So they come in many different types, combinations. So they can be, what you'll hear, and this is where things can get a little bit confusing at times. You'll also hear them referred to as coils. So people say, what coil are you using? Or what probe are you using? And just know that a given probe might have more than one actual coil of wire, but someone may refer to it as a coil. They might refer to a probe as a coil. And so these are going to be, they come in different configurations, different sizes. They have different purposes. Again, some might be more geared towards low frequency, deeper penetration type inspections. Others are going to be geared towards higher frequency surface type inspections. And then a lot of these can be custom designed. So if you have a certain item or object or location that's being scanned regularly, and one of the most common you'll see would be like the bead seat on a wheel half. They'll build eddy current probes with coils that are shaped to whatever it is that you're going to be inspecting. And so they're purpose built. It's not like you can use them on a lot of different things, but it allows you to get a really good contact or a consistent scan of a specific shape. Whereas other probes are more generic in nature and can be used for scanning different areas, but the trade-off is that they may not be as steady. They might wobble around a little bit more, and so you get some error or some noise in the signal in that case. So what do some of these look like? So the first one you're going to have here is for flat surfaces. So the ones shown here, and they can, again, probes can come in all kinds, flat. We'll look at pencil probes, bobbins, encircling, and hole probes. But the ones shown here are spring-loaded. So these are a flat probe. They're designed for a flat surface. The majority of this circle is not the probe. So the probe is just the lighter gray portion in the center of each of these. Okay, where the black surrounding it, the black circles surrounding it, that is purely basically a plastic surface to help brace or hold the probe steady, help you keep it steady. And then the actual coil, the actual probe portion of this in the center, the lighter gray, that's mounted on a spring. And so when you push these against the part, you hold that outer kind of flared piece to the part, and then the spring holds the coil tight or firmly against the surface of the part. And so these are kind of the easiest to use. Here's a picture pointing to that. These are the easiest to use, where they tend to have the least amount of error in the signal. They have the least amount of kind of extraneous indications and that kind of thing. But you know, the trade-off here is that you can't necessarily get the coil itself in tight in like a corner or something of that nature. And again, they can only be used on flat surfaces or a very, very shallow curve. So you know, if you're doing a curved surface like a fuselage, or if you're trying to get in an area where there's a change in geometry in the part, you're not going to be able to really get these probes in there super tight. Some probes can have some different things in them in order to do it, and these probes that we were looking at here tend to utilize this, and that is, we've got the spring-loaded part, but then we also can have probes that are shielded. And so when you're working with these, where there's a lot of material surrounding the coil probe itself, they often have a shield surrounding it as well, because you can't get them in tight to areas. So they'll have a shield that helps to kind of it kind of focuses or controls the spread of eddy currents so that they stay directly underneath the probe. And this avoids some of the effects of things called edge effect, which is when you bring a probe near the edge of a piece of material, you'll start to pick up that change in material, right? You've got metal there, and then next to it is essentially air at the edge, and so it'll cause changes in induction as you do edge effect. It can improve the sensitivity because it's focusing in that area directly below the probe. But as you saw, the increased diameter means we can't get the coil itself as close to certain features or geometry of the part as we could if it didn't have that shielding and that extra space around it. The next kind of basic probe we have is small diameter coils, and these are also often known as pencil type probes. They look like they would be used in pencil probes. And so these are our higher frequency. So the smaller the probe, typically the higher the frequency it's run at. And then as you get into bigger coils, those are going to work more with your lower frequency setup. So smaller coils are operated at high frequency. They have a fairly shallow depth of penetration, which makes them good for, they're very sensitive. You can find those surface flaws, but you're not going to be looking at anything down inside the part. You're not going to be looking for backside corrosion or anything like that. But what that does do is we get rid of all that extra material around the outside, or the things that help us hold them more steady. And they give you good access to small areas, and you can get them into radius corners and that kind of thing. So during lab, you will look at finding cracks in like radius sections of parts, and you'll use these type of coils to do that, these type of probes to do that. By being small, they also reduce edge effect because you basically have to get them closer to an edge. They can fit on a smaller surface without part of the probe hanging over an edge, over like that. So you that. But a disadvantage is because they're so small, it's slow coverage. You can kind of think of it like when you're, if you have like a drawing or something like that, or someone's coloring, right? Colored pencils take a lot longer to color in an area than a big fat marker would. And so, they have that slow coverage in that case. Some coils are larger, and these are kind of the opposite. So they're operated at those low frequencies, and they give you that better depth of penetration. But they're not going to be as sensitive to small flaws, so they're not really going to be as useful for the surface flaws. So best for subsurface flaws, and the most common subsurface flaws that we're going to be looking for is that backside corrosion. Because we're also looking for larger flaws, they're larger subsurface flaws, these probes cover a larger area at the same time as well. And so, again, there's trade-offs, and you're kind of going to be balancing these different goods and bads, or positives and negatives of each of the items you're working with. Here's an example of one of those specialty probes on top. This is called a profile probe, where they're made to fit a certain area. And they're designed for a specific use. So in this case, you probably recognize that's a bulb type connection in an engine part. So this is where you would have like a turbine or a compressor disc, and you would have blades that are held in with a bulb. And so you can see in this top picture that bulb shaped probe is able to get a really good tight contact with the bulb shaped slot that the blades would key into to do inspections of those. And that's a pretty important area in aviation that we do. That's one of the prime uses for this, is in engines, is looking at compressor discs and turbine discs, fan discs, to check for cracks in these areas so that we don't have a fan failure or a turbine failure where the blades come off. Below that is another type of probe, or what's called an array. An array is where you have multiple coils, and they can be arranged in all kinds of different patterns. In this case, they're kind of 2 rows. But with certain eddy current testers, they're able to drive all these different coils together, and you're able to scan larger areas, or in some cases, you can even do like an imaging. It can create a 3D rendering of what you're looking at. And I've got a video of that I'll show. That's pretty cool. That kind of shows how these things work. Here on the top, we've got a hole probe. So the probe itself there's a very small, this is a small diameter coil. There's a small diameter coil on one side of this kind of ball end right here. And so these are designed to fit a specific size hole. And you slide this probe into the it could, like a bolt hole, for instance, and then you rotate it around. And that probe or that coil that's on one side, you rotate around to look for cracks that might be forming at a bolt hole or a rivet hole or something like that. Obviously, a rivet hole, you'd have to remove any rivets that are in there, but that's not uncommon. There are times where we have to remove rivets, do an inspection, and re-rivet something. Or we have to, like a wing spar, remove the wing spar bolts one at a time, inspect the hole, reinstall the wing spar bolt. So, and in this case, they can be turned manually. You can put them in and turn them. Or what you have oftentimes in industry is there's like a little motor, a little holding fixture that you can attach to it that will rotate it automatically. You press a button and it does one full rotation to check for that. Below that's kind of the opposite, an encircling probe or coil. So in this case, instead of it being a coil that you put next to something, for an encircling probe or coil, you actually, the coil in this case is wound around this white plastic piece. And so we put if we need to check things like tubes, rods, other cylindrical, or they even make versions of these in different shapes. If you have like an extruded object that you need to inspect, it's a coil that wraps around, what it is. And so you can slide this, in this case, the white plastic piece that's got coils of wire running through it. You would slide it along the length of the rod or the tube or whatever the object is. And you would look for changes in inductance in that coil that would be caused by things like cracks or even corrosion on the inside. If you're looking at like a tube, these are often used to find interior corrosion on the inside of the tube. And so coils like this can be used in that manner. A few more. So on top here is a bobbin style probe, a couple different bobbin probes. And so now, we had the previous one, the encircling probe, is made to go around the outside of a tube. A bobbin probe is designed to go through a tube or through a pipe. Okay, and again, these ones are circular, but if you have like a square cross-section tube, they make square versions of them that can slide through a tube. And in many cases, these will have multiple coils or even arrays. So what you can see on the one on the right is, my pen, the one on the right here, you can see in the front half, there's a row or a ring of several small coils that encircle the probe, right? And then a little bit further up on the bobbin, you can see there's actually two coils that are turned 90 degrees and are wrapped around the part. So it's actually going to create eddy currents in different orientations to look for different cracks. The other thing is you have the small circles that are kind of to the left. They might be able to be run at a high frequency, looking for, looking at the surface, the inner surface of this tube, while the large coils that wrap all the way around to the right, they may be running at a low frequency to do a more depth of penetration, to look through the wall instead of just on the surface. And so they make all kinds of these where they're different combinations or specialty arrays that allow you to do all kinds of specialized inspections. And they make versions of these. If anyone's seen oil pipelines, they make some versions of these that are 18 to 24 inches in diameter to run through like giant oil pipelines and stuff like that. So pretty versatile, a lot of different ways that you can set this up. I got a question here real quick. So those are our bobbin probes on top. And then on the bottom here is some pencil probes. Now you can see there's a few of the spring-loaded probes in this picture too. But the four on the left here are different types of pencil probes. And so some of them, like the far left here, it just looks straight ahead. It's just got a little circular coil on the very tip. And then you can see the second one over. It's actually the same probe. Like these, the three here are the same probe. They're just the coils mounted in a different way. You know, so one is straight on the tip. One of them has kind of a 90 degree. One of them's got that funky gooseneck with the 90 degree. But they're all like those three probes, the coils inside of them are identical. They're just, you know, maybe one is easier to rotate or get into a certain area, so you can kind of pick and choose depending on where you are on the part and what you're looking for. And then the two, you know, then we've got the spring or the pencil probe that's got a little bit more of a plastic kind of grip on it, and then the two spring-loaded probes you saw earlier. So again, those are going to be, you know, they're all fairly small coils. Those pencil probes are all small coils. So they're going to be designed mainly, this is the kind of probe you would use to go around like rivets or other things to look for surface cracks in sheet metal or thinner materials. So those are kind of the physical setups. Now we need to look at the probes themselves and the coils inside of them. Operate in different ways. They're run in different ways. And so there are modes of operation where we have to match how the coil behaves, how the coils inside of a probe behave, to the signals we're looking for on our tester. And so they break down into, you can see I've got 4 things here, but really there are 3 types of coils. And then the fourth one, the hybrid, is a combination deal. So the first type of coil we'll talk about are what are called absolute probes. The second type we have are called differential. The third are reflection. And then you can see there's just a standard reflection, then there's a reflection differential. That's kind of a hybrid probe. And then you can have probes where there's combinations of any 2 or even all 3 types of coils in them. And so you have to set your equipment, your tester has to be told, either you have to tell it to, or newer ones, they can actually auto sense what type of coils you're using, what type of probes. And so you have the modes. So like on our testers, you can select between absolute, differential, or reflection probes. And then if you have a hybrid, you have to know which mode it's supposed to operate in, you know, which one that it should look at. And so the probe type, it can be defined by number of coils, how they're wired. You know, things can be wired in series or in parallel, or a combination of the two. You know, you might have a couple of coils in series and then another one in parallel. And then also, you know, the simple version I showed earlier, where it was one coil creating the magnetic field, which creates the eddy currents, and then those eddy currents are creating their own magnetic fields that are being picked up by the coil. There are versions where you can have 2 coils. You can have what's called a driver coil. That's what you're sending power to. It's creating the eddy current. And then a pickup coil would be sensing those eddy currents. So there are versions that have different setups in them. So we'll look at a few of those here. So the simplest form is called an absolute probe. And this is what was shown in my earlier examples of a single coil that generates the eddy currents and then also performs the sensing function. These tend to be small. They are used for flaw detection. So versus there's some other, you know, you can have them, they can also be used for conductivity, metal sorting, alloy content, but for aviation, they're used for flaw detection and in-service inspection. And one of the things they can have is they are sometimes wired with a second air-loaded reference coil, because in addition to, you know, the metal in front of a coil, the coils are actually can be affected by air temperature. And so they'll have a coil, even a simple absolute probe with a single coil, a single measurement coil, driver measurement coil, may have a second coil inside of it in order to kind of compensate for some of those temperature changes. And so what one looks like, here's an example of a pencil probe. And as you bring it across, you'll see this image looks very similar to the images I showed, you know, earlier when I was kind of explaining how the eddy current device works and how it indicates. Is that you can see here, they've taken a probe, they started at the left. So A, what they're showing here is A is where they physically set the probe down. Okay, so we physically set the probe on the part. And what happens as we bring it close to the part, as you go from A, which is the coil in the air, to B, the coil sitting on the part, the indication is going to go from A to B on this graph up here. Or on the one on the right that's showing more of a display, that's this one coming straight from the left. And then it goes to what's called our origin point, which is B. And our origin point B is the kind of the standard is what does our screen look like when the coil is sitting still in a known good position. Okay, and it'll just create a dot on the screen. Because remember, this screen is drawing essentially an image of the impedance as it changes over time. So if we're holding our probe still, we're keeping it one position, that drawing, that dot's not going to move. It's going to remain at the origin point. Then as we start to slide the probe, in this case from left to right, you can see when it goes across C, there's three cracks here shown at C, D, and E, C being the smallest. You can see as we draw it, as we bring our probe across C, what's going to happen is it'll start, as we start to approach C, or before we approach spot C on the block, this is a metal block, the crack standard. As we start to go across C, the point on our screen is going to move out. And when the probe is centered over C in this case, then we'll be at point C, which I've kind of drawn in red there. And then as we continue to move from left to right, our indicator is going to move back to the origin point, move back to B. Okay. And then the same thing happens. We'll keep moving it along the surface from C to D. And when we get to D, our pointer or our indication will be at B, right? But then as we approach D, our pointer is going to start to move out. And when we're centered over D, we'll be out at this end here. And then it's going to move back down to B as we go past it. Okay. And when the probe is anywhere between B and C, when it's anywhere between C and D, or anywhere between D and E, where it's not near one of those cracks, our probe is going to show the point down at B. Okay. And then as we keep moving it from left to right, we're going to approach that crack E over here, our deepest crack. And as we approach, our pointer is going to move out. It's going to work its way out. When we're centered over E, it'll come out to E. It'll kind of stay there. And then as we continue to go past, it's going to work its way back down, and it's going to end up back at B at the bottom. Okay. So that's how we can kind of get the idea. So what'll happen is with a crack standard, I mentioned when we started this that we have to have a standard. And so what we can say is, okay, if we have this standard, and if we say C is 10 thousandths of an inch deep, and we say D is 20 thousandths of an inch deep, and we say E is 30 thousandths of an inch deep, that can now allow us to essentially measure a crack. Because if we keep going and we go over an unknown crack or an unknown thing, if we get the pen's not working, there we go. If we get an indication that comes up and comes back down somewhere between D and E here, in my example, I said C was 10 thousandths, D was 20, E was 30 thousandths. If that's halfway between, you can say, yeah, that crack is roughly 25 thousandths deep, right? It's more than the 20 thousandths, in this case, D. It's less than the 30 thousandths E, so it's about halfway. It's probably about 25 thousandths of an inch deep. Okay, and that's where our reference standard comes in, is so we know what we're looking for. And we know our tester set up correctly, so we can see the different flaws that are expected. But then we can also use that to kind of make a judgment on how deep or how big those flaws might be. The next type of probe we have is a differential probe. And so a differential probe, it kind of acts like a bigger, absolute probe. You basically, in a differential probe, you have two active coils. They're both powered. Okay. They're typically wired in series, and when you have inductor coils like this wired in series, they basically act as one larger probe. And so what then happens is a signal or a flaw, it's going to first show up in one of those two coils. And then as you keep moving, it's going to show up in both coils. And then as you continue to move, it'll show up in only the other one. And so that kind of, and they're wired in series, but they're opposite wound. And so it'll cause your indication to kind of go back and forth rather than just up to a point and back. These are very, very sensitive. Okay, they're more sensitive than an absolute coil, but they're sensitive to instantaneous changes. If you have a gradual change, like say you have a piece of tapered material, think of like a doorstop shape, right? And if you're moving your coil along it, it may not pick up more minor changes in geometry, such as like a minor taper. The nice part though is these are more forgiving. When you use an absolute probe, any little wobble shows up as indication. That little pointer moves around the screen. When you use a differential probe, it's not as, you don't get as much noise in your signal from a little bit of wobble or a little bit of unsteadiness. And so they're good for that. The other issue you can have is if you have a flaw, if you're looking for, like corrosion tends to be a larger area flaw. If the flaw is larger than the coil face itself, it can actually be hidden. You may not even see it. It's kind of similar to that tapered property. So these are really good at finding, things like cracks or kind of very small, narrow, isolated things, but they're not going to be as good at finding more widespread damage or things like that. And so if we have a differential probe, here's what one looks like. On the right, you can see kind of the wiring of it. As I mentioned, it's two coils. They're wired in series, but they are reverse wound from each other. So they're going to induce opposite currents in one another as we go. Those eddy currents are going to induce opposite currents in them. And so this shows if we take that coil, that probe that has two coils, and we run it across a flaw, this A, B, C, D, E, it's just showing this probe being run across a crack and what kind of an indication you might get. And so in a real balanced, kind of perfect scenario here, you can see it kind of creates this infinity symbol, and you can see the progression of that here. So we start with our probes are not over the flaw in A, and then as one of the coils starts to get over the flaw, that's going to pull the indication one direction. So in this case, it pulls it off to the right. Then as we come back, as both coils start to get over the flaw, they're going to be balanced with each other again. And so it's going to pull that indication back to that neutral point, back to that center point. Okay, so it made this little loop out to the right. Then as we continue to move it, that because the coils are wound opposite of each other, it's going to pull the indication, those eddy currents are going to cause the indication to go the opposite direction. And so you can see it loops out to the left. And then as we get past it and get back over a good area of the metal in E, that's going to come back to its neutral point. Now that's a real balanced, like ideal situation. You can see here on the display, oftentimes you don't get those two coils to go perfectly evenly across whatever it is you're searching for or whatever it is that you found. And so it's not uncommon for them to be kind of a line with a little loop at the end, like shown here on our differential probe. Next probe type we've got is a reflection probe. And so this is another probe that has two or more coils. But now we have something called a driver coil and a pickup coil. And in this case, then one coil or one group of coils is powered, while a second coil or group of coils is unpowered. And so the powered side is used to generate the eddy currents. So we run current through a coil that creates a magnetic field. That magnetic field goes into the part. That magnetic field hitting the part causes eddy currents to form. Those eddy currents forming are going to create their own magnetic field. But then instead of going back and looking at how it affects the coil that we're powering, we look at how it affects a coil that doesn't have any current running through it. Basically, it's gonna cause a current to flow in a separate coil. And so that's kind of how this works. So that's where it gets the term, so the reflection or driver pickup. And in this case, what's nice about that is, when we have a single coil or when we have two coils that are both powered and both pick up, they may not be ideal for generating eddy currents. They may not be ideal for detecting eddy currents, but they have to be able to do both, right? They're okay at both. With a driver pickup coil, a reflection probe, you can make your driver coil larger and able to put out a stronger magnetic field, right? And run more power through it. But then you can have your pickup coil tend to be small and sensitive. Okay, so you can put a lot more kind of energy into the part and then have a lot more sensitive way of detecting any changes in what comes back, in that signal coming back from the part. And so these are, again, very sensitive. They're very good for that, but it's a more expensive coil. And you have to have, your older eddy current testers weren't able to do these. They didn't have the two kind of channels. They didn't have a way to send information on one channel or send power on one channel and then receive information on the other. So you have to have a tester. Any modern day tester is able to run in a reflection mode. It is able to do driver pickup. And so these can look all kinds of different ways. So here's just some examples of, again, a reflection probe going across a crack. In some cases, they'll show up and it'll look very similar to an absolute probe, like it's shown on the top left. In some cases, they'll behave a lot more like a reflection probe, as shown in the top right. Or you'll get, most commonly, is a combination of the two. So you can see these are kind of, the lines are very similar to an absolute probe, but they've got loops like you get from a reflection, or you get lines like an absolute probe, and you get loops like a differential probe. I'm drawing a blank there. And so that's kind of what you get with your differential. And so then, from there, we can specify things even more. And so hybrid probes are coil arrangements that's not standard or typical. And so we can combine different versions of these, or they might be special configurations of absolute, differential, and or reflection. And then on top of that, you can add things like, maybe you put a couple different size pickup coils or a couple different size driver coils in, so you can run them at different frequencies. Your testers, multi-frequency testers, can be set up where they send a high frequency, low frequency, high frequency, lows, and they're switching back and forth several times a second. And it's doing that. So there's all kinds of like real high-tech stuff that can be done. And most of these are specialized application, right? There's something very specific we're trying to find. An example of that is fan discs that have a probe. This is the engines that are on the 737, not the MAX, but the previous generation, or the A320 family of aircraft, are the Engine Alliance engines, and they've had problems with fan blades coming off. And so they have to do fan disc and fan blade inspections, and they use some hybrid probes that are shaped specifically to match the root area of the blades, and they can look for all kinds of different cracks possibly forming in order to prevent an uncontained fan failure. And so these are, again, they can be pretty high tech and very specialized. So if we look at the wiring on these, and I've got a little more blown up version here, you can see, so the top left here is kind of your simplest probe. This is an absolute probe. So it's got the test coil. The detector would be your screen, your tester. Okay, so they just show where they showed detector here, the triangle, that's an amplifier that would be outputting to your display screen. And as I mentioned, this one shows, so the OSC, the oscillator, that's our AC frequency going in. That's driving the coil. The detector is sensing changes in impedance. And then this one has a reference coil as well for the temperature changes. Okay. You can see another coil type. Another name for a differential coil is a bridge type probe. So the bridge type probe here is also, you could call it, it's your differential coil. So that's in the middle at the top here. So this is also differential. I don't have a way to type. I wish I did. Differential. So there's a differential coil, and it's showing those two coils, those two test coils that are kind of opposite. This one doesn't show a temperature compensator on it at all. Okay, but you can see in this case, the oscillator, the AC is being sent to both sides, to both coils at the same time. Okay, so that's what makes it a differential or a bridge type coil. And then the reflection probe is shown on the right, and it looks very similar. You can see they still have these coils wired, but in this case, the AC current's being sent to one coil, and then don't miss that there's a ground down here. Okay, so they're not wired. That AC current's not going from the left coil to the right. It's gonna connect to the ground on there. And then the coil there on the right, the pickup coil, goes from our detector, to the ground is where our circuit runs. Whereas over in the differential style, both coils are being powered and both coils are being sensed by the detector. And then as you get down below, there's some different kind of combinations of them. So, a differential, a bridge differential or a differential, another type of differential coil. You can see it's very similar to the bridge type. And then finally a reflection differential, which shows a setup where you have both going on. So you've got a reflection type coil or a driver. So you've got a driver on the left, and then you have two pickups that are in parallel that kind of give you that reflection set. And then the three coils, two of them are related to pickup, one of them is related to driving. So these come in all different kinds of wiring schemes. This is only a few of them, but they, again, they can be wired all different ways. But the simplest three you're going to see are across the top with the absolute on the left, the differential coil in the middle, differential probe in the middle, also known as a bridge type, and then the reflection probe on the right. It kind of gives you an idea of how they're wired. Next slide I have is getting into array probes. And so I'll show this video next time. We'll start out class with the video, and then I've got a little bit more on probe loading, shielding, and that kind of thing, and that'll wrap up our eddy current.